Alright, let me take one more lecture video before going home. And in this video, I'm going to talk about cost minimization. So, before giving you motivation about why we have to consider cost minimization separately from the profit maximization problem, let me first introduce the problem itself. So the cost minimization problem has the very similar structure as the expenditure minimization problem. So think about the firm producing single output. So we consider single output technology. In order to produce certain output, firm has to employ input. So now we can regard the firm as a consumer. Consumer, the consumer employing, so demanding several inputs in order to produce Q. And for producing amount of Q, the necessary cost can be written this way: W dot Z. Once again, W is the input price vector, and Z is the input vector. So their dot product is going to be, so it's going to be the total cost of employing this amount of input given input price vector W. And the firm attempts to minimize the necessary cost, in order to produce this amount of quantity. So, just think about the expenditure minimization problem. Consumer wants to minimize the expenditure necessary for attaining certain level of utility. So it has the very similar structure. Firm wants to attain this amount of output. So the firm wants to produce this amount of output and list. So given this constraint, what is the minimal cost necessary for production of this amount of quantity? So that gives us cost minimization problem, in short CMP. And the solution to this problem is, it depends on two parameters: input price vector W and the target quantity Q. And because this input demand depends on the target quantity, so it is known as the conditional factor demand function. It is a factor demand function conditioned on target quantity Q. And then if we substitute the solution to the objective function into the objective function, so the dot product between the input price vector and the conditional demand function is called the cost function. Just like the conditional factor demand, the value function also depends on these two parameters. Now let me discuss why we have to study cost minimizing firms' behavior. So first, it provides another angle of looking at the supply behavior of a firm. So it turns out that there is a nice duality between conditional factor demand and unconditional factor demand, just like a duality between Lagrangian demand and Hicksian demand. So we are going to study this duality in the live lecture next Wednesday. And furthermore, unlike the profit maximization problem, this cost minimization does not rely on the market constraint. What does it mean? So if we go back to the formulation of a profit maximization, in case of a single output technology, in this formulation, it is assumed that firm faces two constraints. The first, technology constraint. Given these inputs, firm can produce up to f of z and most. So that is so the firm faces such a technology constraint. Additionally, the market constraint. By producing this amount of quantity, firm can attain this amount of revenue. And this revenue is given by a unit price of output times f of z, the quantity produced. So that there is another assumptions in this formulation. No matter which quantity firm produces, market price is fixed. But if you study the industry organizations, there are several market structures, from monopoly to oligopoly and the competitive market. So in competitive market, it is assumed that market price is independent of the firm's production schedule. But in case of a monopoly or oligopoly, this market price also a function of the production schedule. Okay, so in the formulation of a profit maximization, we have two underlying assumptions: the technology constraint, so that determines the maximum output the firm can produce as much as f of z, and the market constraint. If the firm once the firm produces this amount of output, it has to sell each unit at the price of P. Okay? That assumption is valid only under the comparative market assumption. So only under some structure, some special structure of market. Okay? So it does not hold, for example, monopoly or oligopoly. Okay? But in contrast with the profit maximization, there is a no output price in the formulation of CMP, meaning that this cost minimization problem is independent of the market structure. We can apply the same problem to the monopoly or to oligopoly or to comparative market. Okay? So that is one major merit of analyzing firms' behavior using cost minimization problem. Okay? All right. So the way to find this conditional factor demand is from the Lagrangian multiplier theorem. And so now the associated Lagrangian can be written as L is W dot C. Okay? And then we need a multiplier for this constraint f of z larger than or equal to q. Okay? So first we change this inequality into the form f of z minus q larger than or equal to 0. Okay? And then because we analyze the minimization problem, so we change the sign of the multiplier to minus. Okay? So for a maximization problem, we put the positive sign here in front of the multiplier. In case of a minimization problem, we put the negative sign. Okay? Or you can change the form of the inequality as the something is less than or equal to 0, but that is slightly confusing to me. So usually I write down the Lagrangian into this form. So without changing the inequality form, okay, I change the sign of the multiplier from positive to negative. Okay? But you may have your own taste, so it does not matter. Okay. All right. So the Lagrangian multiplier tells us if we have an interior solution, because every vector z, so every component of this vector z is a positive constant, non-negative variable. Yeah. So now interior solution is going to be every vector, every component in this vector is strictly positive. Okay. So if we have an interior solution candidate, so this z star source is a solution to the CMP, and we must have the following stationary condition. So now the choice variable for this firm is going to be if the firm faces L-1 dimensional input, so L-1 different inputs, then so in case of two inputs, okay, then let me start with the two inputs, z1 and z2. Okay, and the first of the condition is going to be partial derivative with respect to z1 and partial derivative with respect to z2 should be equal to 0. Okay, and then for the from the first condition we have w1. Okay, that is from the this objective function. So if we take the partial derivative with respect to z1, we obtain w1, and minus lambda times the derivative of the expression in the parentheses gives me so partial derivative of f with respect to z1. Okay? So that is a marginal product of input 1. So we put this equal to 0, and the second condition tells me w sub 2 minus lambda the marginal product of input 2 should be equal to 0. Okay. So we can express this condition in terms of matrix forms. So W1 and W2 should be equal to lambda times gradient of function f at the solution z star. Okay. Or we can divide one condition by the other. Then we obtain. So first, for example, if we divide the first condition by the second, we obtain W1 over W2 equals MRTS between 1 and 2. Okay. So we have two equivalent conditions. So in terms of matrices, input price vector and gradient vector must indicate the same direction. Okay. And remember, gradient of function f indicates that in which direction the function, the output is increasing at the greatest ascent. Okay, just like the the gradient of a utility function. So just as the gradient of a utility function indicates the direction in which the utility function is increasing at the greatest ascent, the gradient of a production function tells us the vector, the direction in which the firm can increase the output at the greatest ascent. Okay, and the W is going to be a perpendicular vector to the isocost. Okay? So this W vector and the gradient should indicate the same direction. Or we can apply the familiar tangent condition. Okay? So at the conditional factor demand, so the slope of the tangent line. So the slope of the tangent line that is given by MRTS to the isoquant should be equal to slope of the isocost, that is W1 over W2 in case of two inputs. Okay, so if we think, so we have seen this. So we had the same condition regarding the profit maximization. Okay, in case of two inputs and in case of single output technologies. Going back to single output technologies. The first of the condition for profit maximization was this. Yeah, as exactly identical with the cost minimization problem. Okay, that is not surprising because so if we compare cost minimization and the profit maximization, so profit maximization was P dot, so P times F of Z minus W dot C. Okay. So maximizing this quantity given target quantity Q. So now we can replace this F of Z with Q. Okay? And maximizing profit is totally equivalent to minimizing this cost. Okay? Given this target quantity Q. So that's why we have the same optimal condition. And as usual, the Lagrangian multiplier can be interpreted as the marginal variable relaxing the constraint. So here, we have this constraint. Okay, suppose that we reduce down the target quantity by 1. Okay, so we reduce by Q minus 1. So we reduce down the target quantity to Q minus 1. Then the necessary cost will be will decrease, and that decrement of that cost is captured by the Lagrangian multiplier. Okay, and that is consistent with the marginal cost of production because we have a cost function of the value, okay, as the value in the CMP. Okay, and if we reduce down, so if we readjust the target quantity, so reducing down by 1, then how much cost we can save? Yeah, that is a marginal cost of production. Yeah. So we have this Lagrangian multiplier. So here's one example to remind you of how to solve cost minimization problems. So we have familiar Cobb-Douglas technologies. So A times Z1 to the alpha times Z2 to the power 1 minus alpha. Okay? And we want to derive the cost function and conditional factor demand functions. Okay? So yeah, so we can first write the Lagrangian. So L is going to be our objective function. So now we're considering two inputs, right? So the cost is going to be W1. So input price of the input price of input 1 times Z1, and the price of input 2 times Z2, demand for that input, and minus lambda. Okay, and the given constraint was f of z is larger than q. Okay, so the firm can wants to produce and list this amount of quantity. So that's going to be, in this example, a z1 to the alpha z2 to the power 1 minus alpha minus q. Alright, so taking partial derivative with respect to z1, we obtain w1 minus lambda. Okay, and the partial we have to put the partial derivative of this with respect to z1, that is a times alpha z1 to the power alpha minus 1 and z2 to the power 1 minus alpha, and set it equal to 0. And derivative with respect to z2, the other choice variable, gives me w sub 2 minus lambda. Now we put the partial derivative of this with respect to z2. So a times 1 minus alpha z1 to the alpha and z2 to the power negative alpha, and set it equal to 0. Okay, so you can solve this using the matrix form, or you can simply divide one by the other, but let me take the second approach. Okay, so let me move these two terms to the right hand side and divide the first equation, so the first condition, by the second. Then we obtain w1 over w2 equals lambda will be cancelled, right? And then we have MRTS. Okay? And then MRTS for this Cobb-Douglas simplifies to this expression. Okay? So if you find the ratio between these two, you're gonna get this expression: alpha z2 over 1 minus alpha times z1. Okay? Because this is a simple algebra, so let me skip that. All right, and then so I can solve this equation for z1. Okay, so multiplying both sides by z1, okay, and then dividing by w1 over w2. Okay, then I obtain, so I have a solution for z1. So z1 is equal to this guy times z2. Okay, and then let me call this w hat. Okay, so then I can simplify the expression w hat times z2. Okay, so w hat indicates this fraction. Okay, and then one more thing we can observe from the first order condition. Okay? So the first order condition requires that w1 is equal to this guy. W1 is equal to this guy. And the second condition requires W2 be equal to this guy. Okay. So, so in light of these first order conditions, two first order conditions, now we can say lambda must be strictly positive. Okay. Lagrange multiplier should be strictly positive, because if that is equal to 0, okay, because input price is a positive, W1 and W2 are given by some positive constant, so there is no way to satisfy this condition. Okay, so as long as input prices are positive, strictly positive, so the multiplier must be strictly positive as well. Okay, so by the complementary slackness condition, if the multiplier is strictly positive, then the constraint must be binding. Okay, so the given constraint was, this guy should be equal to 0. So it is originally put as alpha z1 and z2 larger than or equal to q. So originally it is given by inequality constraint. Okay? But the complementary slackness condition tells us if the multiplier is equal to 0 or is strictly positive, then this inequality constraint is held with an equality. So with an equality, okay, so we have this condition. Okay, and what can I do using this condition? I can substitute this one, so w hat z2 for z1 here. Okay, then I'm gonna have equation for z2. Okay, and solving for z2 gives me this one. Okay, and once we obtain the expression for z2, then we can substitute that expression here. Okay, and that gives me the conditional demand for input 1. Okay, that is right here. Okay, so let me skip the details because it's a simple algebra, but yeah, you can check by yourself. The conditional demand should be like this. Okay, and then on the next slide, I put the some basic properties of cost functions. So we obtain the conditional demand, and the way to find the cost function is a piece of cake. So C W comma Q is going to be W1 times this Z1 star. Okay, so I can substitute this conditional demand for input 1 and plus W2 times Z2 star. Okay, so just like the conditional demand, this cost function is going to be a function of input price vector and the target quantity Q. Okay, and you can simply check that each conditional demand is a function of price vector and the target quantity Q. Okay, and then so one more thing you can observe is this Cobb-Douglas function is given by z1 to the alpha and z2 to the power 1 minus alpha. So the sum of two exponents is given by 1. It means this technology exhibits CRS. Okay, so in case of CRS, the corresponding cost function is going to be linear function with respect to Q. Okay, so it should be linear with respect to Q. Okay, so you have a there is a one-to-one relationship between return to scale and the shape of the cost function. Yeah, so let me summarize here. If technology exhibits CRS, then its cost function is linear in Q, target quantity Q. And if function production technology exhibits IRS, yeah, that means by producing more and more, the firm can produce more efficiently. So cost function becomes concave in Q. And finally, if the production technology exhibits DRS, then cost function is convex in Q. Yeah? So if we draw the cost function with respect to Q, so regarding this cost function as a function of Q, so we pin down input price fixed. Okay, and then describing this change in cost with respect to change in Q, target quantity. In CRS, it's going to be linear. That does make sense. And then in case of IRS, it is increasing but at a decreasing rate. Okay, so by producing more and more, the firm can produce that target quantity at a less cost. So that means production line becomes more efficient. It exhibits IRS. And in case of DRS, firm is convex. The cost function is convex. So it looks like this. By producing more and more, the firm incurs a higher cost, okay? Meaning that production line becomes less efficient. Okay? All right, and then general properties about cost functions. So I think these are quite similar to the properties of expenditure functions as well. So first, cost function is homogeneous of degree 1 in input price vectors. That is from the structure of the cost minimization problem, because the cost minimization problem is linear. So that is a linear with respect to W. Okay, if we scale up W by alpha, okay, the total cost will increase alpha fold. Okay, so cost function is homogeneous of degree 1 in W, and if we set the target quantity higher and higher, naturally the necessary cost is going to be strictly increasing. And with respect to input prices, it is non-decreasing. So for example, if the W2 increases, if the firm does not use this input for production, then cost remains the same. Okay? So it cannot be, so it can be, so it takes the same value. I mean, it may be non-decreasing, but it cannot be, say, increase, or it cannot be, say, decreasing, strictly decreasing in W. Okay, then the cost function takes the different shapes depending on, so with respect to Q, so it can be convex or concave with respect to Q, but with respect to W, it should be concave. Okay, let me leave it as an exercise. So just like the just as the expenditure function is concave with respect to price vector, you can show that expenditure function is concave with respect to input prices. Okay, and finally, Sheffer lemmas. Yeah, so just as if we take the derivative of expenditure function with respect to price, we obtain the Hicksian demand. And if we take the derivative of cost function with respect to input price, say input price for K, then we obtain the conditional demand for input K. That is immediate from the envelope theorem again, because the way to find the partial derivative of the value function, we take the derivative of the objective function with respect to WK. Yeah, because objective function is W dot Z, and its partial derivative with respect to W sub K gives me G sub K. Okay? And then we substitute the optimal solution, that is the conditional demand. Okay? So partial derivative of a cost function with respect to input price gives me conditional demand. Okay, so that is a Sheffer lemma. So I quickly went through the cost minimization problems because it has a very similar structure to expenditure minimization problem we studied in consumer theory. But whenever you have a question about this, feel free to ask me in the live lecture. And let me stop the lecture videos for the 6th week and see you at the live lecture next Wednesday. All right, hope you enjoyed this video and see you next week.